With the release of ASAP 2013, Breault Research Organization has added a unit cell microstructure model that avoids explicit representations and is both fast and accurate. Microstructure is a repeated geometrical pattern that is placed on a surface to alter the dispersion of incident light. Microstructures are frequently used in backlight displays to direct light from an underlying plastic guide to and through a diffuser and active display. They are also used in illumination systems to shape and direct light from a source to an area of interest. Explicit computer modeling of microstructure is difficult because the number of microstructure elements is often very large, numbering thousands, tens of thousands, or even millions of individual elements that must be defined, visualized, and ray traced. This is accomplished by using a unit cell model, in which users construct a single cell within the repeated pattern of the microstructure. ASAP uses this single cell to simulate the effects of microstructure on incident rays. These effects include refraction, reflection, absorption, Fresnel or ghost reflections, and scatter. Let us look at a simple example in which microstructure is used to illuminate a display. Here we see an edge-illuminated display in which light from 9 LEDs is fed into the edge of a light guide. The long rectangles above and below the row of LEDs, shown here and here, are reflectors that direct some of the wide-angle light from the LEDs into the edge of the light pipe. If we suppress the top surfaces of the display, as we've done here, we see an array of 2,500 bumps molded into the floor of the waveguide. Refraction and reflection from these bumps directs light out of the top of the waveguide to illuminate the display. These bumps are microstructure. If we zoom into the display, we see the individual elements of our repeated pattern. We call these members unit cells. Each unit cell consists of not only the hemispherical bump, but the planar surface around each bump, bounded by a rectangle that divides each unit cell from its neighbors. Unit cell microstructure modeling in ASAP is done by constructing a single unit cell and telling ASAP to apply this unit cell over an entire object. Let's see how this works. Here is the same display we saw earlier, but without any bumps on the floor of the light guide. During a ray trace, we want ASAP to simulate the effects of the bumps, without actually having to place a large number of real bumps on the floor of the light guide. Here is how we do this. First, we construct a single unit cell, centered on the origin, with the z-axis normal to the rectangular boundary of the cell. Here is a script that defines the unit cell. The rectangular boundary that surrounds each hemispherical bump is given here, consisting of a plane with a cutting tube that cuts a circle that allows the hemisphere to fit inside. Below that is the hemispherical bump, shown here. Note that we define not only the geometry, but also its optical properties. We define a media, and we apply that media to each object using the interface command. When we execute this file, here is our unit cell. We see the ellipsoidal bump, and we see the plane boundary surrounding the bump. And if we bring the axes up, hitting the A key in the 3D viewer, we find that the z-axis, shown in blue, is indeed normal to the rectangular boundary. Next, we construct a model of the display without the bumps. Just for fun, let's look at this model and see what the illumination pattern looks like without the microstructure. Here is a script that defines the display without the bumps. Let's execute this script, looking at the display itself and the illumination pattern produced by the display. When we look at the illumination at the top of the display, we see that we are only getting light on the far end of the display and getting nothing out on the front end. We see that a bare surface does not give us light over the entire display. We need microstructure to force light out of the plastic light guide and through the top of the display. Let's look at how we apply microstructure using the unit cell model. It is 4 simple steps. First, we tell ASAP the dimensions of the unit cell. We do this by defining a rectangular edge with the same dimensions as the unit cell as shown here. Here's my edge. It's a rectangular edge with a semi-diameter of 1 unit or 1 millimeter. Next, we insert the script that defines the unit cell. Here is the script that defines the planar structure around each hemispherical bump, and here is the script that defines the bump itself, along with the optical properties applied with the interface command. Third, we use the new microstructure command to define a microstructure model under the ASAP model command. Here's the model command that tells ASAP to begin defining models. Then comes the new microstructure command with several entries. The first entry tells ASAP how to orient the unit cell. In this case, we're defining the reference direction for the local coordinate systems that's parallel to the global x-axis. The second entry is the number of the edge that defines the boundary of the unit cell. This is the edge that we defined here. It's an edge perpendicular to the z-axis with a semi-diameter of 1. And this is the first edge we defined, so it's number 1. The last two entries are the names of the objects that define the unit cell. So in our second step, where we define the unit cell itself, we called the planar boundary UC1, and we called the ellipsoidal UC2. The names are immaterial. We can call them anything we like, but once we name them, we can use those names on the command itself to tell ASAP which objects define microstructure. In this example, there are only two objects, and we define them with an ASAP script, but we could construct an arbitrarily complex unit cell using hundreds or even thousands of objects. We may also define the unit cell in CAD and import the script. Finally, we assign the new microstructure model to the floor of the light guide using the scatter model command. Here's the floor of the light guide, and here's the command scatter model 1, which says to take the very first model we've defined, in this case model number 1, and assign it to this object. This command attaches this unit cell microstructure to this object so that the optical properties of the microstructure are simulated during the ray trace. Now let's execute the script to see what happens. We see that our unit cell model alters the direction of rays incident on the floor of the light guide, directing light out the top of the display and filling the entire display with light. Does the unit cell model give correct answers? To find out, let's compare the results of the unit cell model with the results of an explicit model to see if they look the same. Here is a script for an explicit model. Here is the output from an explicit model, which we may compare with the unit cell model. And we see that the two outputs are very similar. So the unit cell model is capable of reproducing the results from an explicit model, which is much more complicated and takes much longer to ray trace. If we look closely at this result, as well as the unit cell result, both results show large statistical fluctuations because we have not traced enough rays. Let's look at the results of a longer ray trace that uses 100,000 rays per source so we can get a better picture of what the irradiance looks like. This ray trace has already been performed, and I'm just going to show the result. Here is the result from an explicit ray trace that took 45 minutes. We see that the distribution is much smoother, and we can see many more details, but we still have large statistical fluctuations. We can reduce this by either ray tracing even longer, or by doing some averaging, where we average each pixel with its neighbor. I'll do this twice. Now we have a relatively smooth distribution that shows us the characteristics of the irradiance on the display for the explicit model. Again, we compare the results of the explicit model with the unit cell model, and we see that the answers are very similar. demonstrating that the unit cell model is an accurate way to model microstructure in optical systems. The difference is not only in terms of ease of setup, but also speed of execution. The explicit model in this example took 45 CPU minutes. The unit cell model took less than 4 minutes. We achieve an increase of over a factor of 10 in ray trace speed by using the unit cell model rather than modeling everything explicitly. We also avoid having to construct models with many thousands of microstructure elements. So this has been a short overview of just one application, modeling a backlight display of the new microstructure model in ASAP 2013. Other applications for this microstructure modeling capability may include illumination systems, where we use microstructure to produce custom light patterns on work areas, or light pipes for automotive display, or custom diffusers.